Hi, my name is Jihan Abu Halloun. I am a postdoc fellow in Research Group Discovery in the Department of Chemical Engineering at Wayne State University. And our tutorial today is related to how we can run large language models on HPC using GPUs. In the digitalization era and smart manufacturing, companies are harnessing the power of large language models across multiple sectors, including process engineering, fault detection, and process control. While several ways exist for prototyping these LLM models, such as Google Colab, which can be used to run LLMs using GPUs, where GPUs are needed to run LLMs which require heavy computations, such as matrix multiplications. In this tutorial, we're gonna leverage HPC to run an LLM model on GPUs. More specifically, we're gonna use the Wayne State University grid as an example in this tutorial, where we're gonna walk through the WSU grid key instructions in order to demonstrate the simulation of an LLM model on the grid using GPUs. As a result, this talk will be divided into two parts. In the first part, we're gonna give an overview of how to simulate an open source LLM model in Jupyter Notebook using Python code. And in the second part, we're gonna discuss how to simulate an open source LLM model on the WSU grid using GPUs. While a variety of LLM models exist, the open source LLM model from Hugging Face adopted in this tutorial is Llama2 with 13 billion parameters. So what do we mean by parameters? Parameters are the elements within the model that are learned from the training data. For example, Llama2 with 13 billion parameters is more knowledgeable than Llama2 with 3 billion parameters or Llama2 with 7 billion parameters. While large language models can perform a variety of tasks, in this tutorial, the LLM model will be used for text generation tasks. Having identified the LLM model and its corresponding task, in the next slide, we'll be discussing how to simulate Llama2 with 13 billion parameters based on the following YouTube video. So here we can find the link of the YouTube video. Based on what we're gonna discuss the simulation of Llama2 with 13 billion parameters in Jupyter Notebook. In fact, to run an LLM model in Jupyter Notebook, we need first to install the packages needed. And after installing these packages, we will be discussing how to simulate Llama2 in Jupyter Notebook with its corresponding tokenizer, and how to initialize the text generation task, and how we can prompt Llama2 to execute a specific task. So first, we're gonna discuss the packages needed to run an LLM model, which is here Llama2 with 13B parameters in Jupyter Notebook first, and then on the grid. So the first package needed is transformers, since we are dealing with large language models. The other two packages are LangChain and Hugging Face, which are both needed to simulate an LLM. What do we mean by LangChain? LangChain is an open source framework that allows the user to interact with various LLM models and chain an LLM model with other components, such as chaining an LLM model with a system prompt to perform a specific task. And now, what do we mean by Hugging Face? Hugging Face is an open source machine learning and data science platform that provides tools such as pipelines, libraries such as a transformer library, a tokenizer library, and data sets. Additional packages are needed to be able to simulate an LLM model, which is in this case Llama2 with 13B parameters, such as the XFormers library, which provides a set of optimized transformer building blocks that makes the simulation of the LLM model faster with less memory consumption. In addition to the XFormers library, we need also the INOPS library for tensor manipulation. To accelerate the LLM inference and to run LLMs with less memory footprints, we need both the accelerate library and the bits and bytes library. And we'll be talking more about these two libraries in the next slides. Since in this tutorial we are also running the LLM on the grid, we need a tool which is the NB convert tool in order to convert the Jupyter notebook, which is considered as an input, into a different format as an output, but in this case, in our case, it will be a Jupyter notebook too. After discussing the required packages to simulate an LLM model in Jupyter Notebook, the next step is to show how we can run Llama2 with 13B parameters in Jupyter Notebook. For that, we need to perform two things. First, we need to create a Hugging Face token, and then we need to get an approval from Hugging Face to access the LLM model. In order to create a Hugging Face token, we need first to create an account in Hugging Face using the following link. Once the account is created, we need to click on Settings and then click on Access Tokens and then create New Access Token. After that, we can select the type of the token to be created, where in this case, we can select the read type, and then we need to name the token. After naming the token, we can click on Create Token, and then copy and paste the created token in a safe place without sharing it with anyone. After creating a Hugging Face token, the next step is to get an approval from Hugging Face in order to access the LLM model. To get an approval from Hugging Face, we need to do the following. So first, we need to sign in into our Hugging Face account using the following link, and then we need to click on Settings. And in Search Models, we need to type the following LLM model, which is Llama2 with 13 billion parameters. And then we need to fill in a form to get the approval from Hugging Face. Having identified the LLM model, which is in this case Llama2 with 13 billion parameters from Hugging Face, and after getting the approval from Hugging Face, the next step is to set the device. So in this case, we determine whether to employ GPU, which is CUDA here, if available, or fall back to CPU. So CUDA here is a parallel computing platform and programming model from NVIDIA, and it's needed to perform heavy computations such as matrix multiplication. However, dealing with a large model architecture requires more memory to store its parameters and process the data. In order to address this limitation, model quantization can be performed, which will be discussed next. So what do we mean by quantization technique? Quantization technique refers to a compression technique that aims to reduce the size and load the LLM model with less memory. The quantization technique requires a library called the bits and bytes library, which was shown in a previous slide, where, for example, the 4-bit quantization can be used. And that's why we set here load in 4-bit to be equal to true. The quantization technique is done by mapping high precision values, such as floating point 32-bit weight, to lower precision discrete values, such as integer 4-bit, which is the case here. The 4-bit quantization strategy considered here is normal float 4 data type for normally distributed weights. And in this case, we enable double quantization in order to quantize the quantized constants in order to reduce the memory usage. The data type used here for computation is bfloat16, where the GPUs, CPUs use 16 bits to represent a number. So this is like compressing the LLM parameters with 4 bits, but during computation, the parameters are computed using 16 bits to get a higher precision. This is done to promote balance between speed and precision for matrix multiplications during LLM inference. While quantization can sometimes impact the accuracy and capabilities of the model, this can reduce the memory footprints and achieve, in some cases, comparable results with lower precision and less computation time. After identifying the quantization configuration to be able to simulate the quantized version of Llama2 with 13B parameters, the next step is to instantiate Llama2 and load its pre-trained weights. When loading an LLM model from Hugging Face, the following code is used where we need to identify the LLM model, and here trust remote code is set to be equal to true in order to be able to execute custom Python code stored in the LLM model remote repository. However, this requires caution due to the presence of malicious repositories which could contain malicious code that can run on your machine. In our case, loading Llama2 checkpoints from Hugging Face is in general considered as a trusted source, but it's always recommended to verify the repository, inspect the code, and run the LLM model in an isolated environment. Then we have here configuration equal to model configuration, where the configuration class to instantiate is selected based on the model ID and using the HF token that we just created. Since in this case we are running the quantized version of Llama2, we need also to add the quantization configuration that we discussed in the previous slide. In order to automatically determine how and where to load and store the model's weights, the device map in this case is set to be equal to auto. This is often used with another library called the accelerate library, which can take care of managing the model's weights. If GPUs are available, this will help in distributing the model in an efficient way across available GPUs. Since the LLM model in this case is used for inference and not for training, we need to add the following code, which is model.eval. Having given an overview on how to simulate an LLM model in Jupyter Notebook, in the next slide, the simulation of the corresponding tokenizer will be discussed. Before showing how to simulate a corresponding tokenizer, we need to define first tokenization. So the prompt is considered as an input to the LLM, and the prompt here is, for example, a question that is asking what is the capital of US. The prompt is first tokenized, and where each word is mapped to a token ID. So for example, in this case, what is the first token? Is the second token, the third token, etc. So the tokenization is done using a tokenizer that corresponds to the LLM model. In this case, the Llama2 with 13 billion parameters tokenizer is used. This is because the Llama2 with 13B parameters models were trained using this tokenizer, which is Llama2 with 13B parameters. So as we can see here, in order to simulate the corresponding tokenizer, we need to identify the model ID, which is Llama2 with 13B parameters, while using the Hugging Face token that we just created. Having simulated the corresponding tokenizer, in the next slide we'll be initializing the text generation task. So now we're going to show how we can initialize the text generation task. So for that, we need our model, which was discussed in the previous slide with its corresponding tokenizer, and also it's expected to return the full text. So that's why return full text was set to be equal to true. And here the task was set to be equal to text generation, since the task in this case to be performed by the LLM is the text generation task. And also in this case, we can identify the model parameters, which are the maximum number of tokens to generate in the output. And in this case, we set it to be equal to 512. And also we can set the temperature in order to control the degree of randomness in the selection of tokens during the response generation, and in this case it was set to be equal 0.01 since it's close to 0, so it's approximately equal to 0, in order to require less randomness and more determinism in the LLM response. And also we can set the repetition penalty to be equal to 1.1 in order to prevent the LLM model from repeating the same information by reducing the scores of the previously generated token by approximately 10%, which can lower the token's likelihood of being generated again. So having now initialized the text generation task, the subsequent step is to assign the LLM model, which is Llama2 with 13B parameters, to perform a specific task, which will be discussed next. For an LLM model to perform a specific task, an LLM needs to be prompted with a specific persona, which is a type of a fictional user's character. For example, an LLM model can be prompted to act as a simple question generator. However, personas need to be carefully tailored to turn an LLM into an expert in a specific domain or field. One way to guide an LLM model in generating text that aligns with a specific persona is through a system prompt, which needs to be carefully crafted. Since in this case, the LLM model considered as Llama2 with 13B parameters, the default Llama2 prompt style will be shown in the next slide. The default Llama2 prompt style mainly involves a system prompt where a persona is given to the LLM model, and in this case, we are asking the LLM model to act as a helpful assistant that always answers questions, in addition to corresponding instructions where, for example, here we are asking the LLM model to answer the question based on the provided information, where the two variables here are the query and the evidence. And the resulting system prompt will be the default system prompt bounded by sys at the beginning and /sys at the end. And the prompt template, as in this case, will be the combination of the system prompt, which is the following, plus the instruction, and which will be bounded by inst at the beginning and /inst at the end. As a result, the default system prompt will be instruction since system prompt system instruction inst. So this is like the default system prompt for Llama2 with 13 billion parameters. The elaborated prompt is then connected to the LLM model using chains from LangChain to perform a specific task. More specifically, an LLM model will receive as an input a prompt to generate a final response as output, where the prompt in this case is fixed and where the variables here, for example, evidence and query, will be changing. Such prompt templates are important component of LangChain, and an example of an elaborated prompt will be shown in the next slide. Here we show an example of a prompt crafted to ask Llama2 to generate a simple question based on the provided information denoted as evidence using few-shot prompting, where in addition to the system prompt and corresponding instructions, we provided examples in order to teach Llama2 how to generate a simple question based on the provided information. In this case, the evidences used as examples in the system prompt are extracted from the Fever Gold evidence data set. Having elaborated the corresponding system prompt, the next step is to set Llama prompt to be equal to prompt templates, where we set the input variable here to be equal to the variable evidence based on what the LLM will be generating a simple question, and where the template here will be equal to prompt template. The next step is to set the generation to be equal to LLM chain, where we're gonna chain the LLM model with the corresponding system prompt, and then the question that will be generated will be equal to generation.run, where we're gonna pass each time a new information based on what Llama2 will be generating a new simple question. Here we show an example of a question generated by Llama2 with 13B parameters using an information retrieved from the Fever Gold evidence dataset and denoted as evidence. So as we can see here, the question is equal to generate quest, which was defined in the previous slide, and where we pass the new information based on what Llama2 will be generating a simple question. And as we can see, Llama2 was able to generate a corresponding simple question based on the information provided. Having given an overview about how to simulate an LLM model in Jupyter Notebook, the next step will be discussing how to run such simulation on HPC using GPUs.